One class model. Okay, excellent. So classification-based method. So earlier we mentioned that we could actually have the normal data and the outliers to be treated as two different classes and use typical classification algorithms to make predictions when you have training examples. But a lot of times we have training examples for normal class. We don't have complete data set for outliers because we cannot enumerate outliers, obviously. So two-class approach is what all you already know, and the one-class model is what we're going to introduce, the one-class support vector machine. One-class support vector machine is also called one-class support data describer or description. The idea is to use one class and the support vector machines to learn a description of this one class. And then we can use this model. Anything that's fit within this model is a normal class. Anything that's not within the model, it's an outlier. So I think your question is, if we only have one class training examples for a normal class, then how can what are we training? Because we know support vectors was actually finding the division boundary between two classes, right? In this case, one class support vector machines trying to find the ball, hyperball that would encompassate all normal classes. So using this as example, this could be the boundary here, learned. So any dots here could be support vectors for this one class support data description. So all the dots on those edges could be the support vectors, and all those outliers are also support vectors. So the one class support vector classification is to finding this boundary. The process is very similar to actually, so the goal is to minimize the radius here, allow some slack factors, allow some arrows that would make those outliers possible, become support vectors surrounding this decision boundary. Okay, so one class support vector machines does not need labeled class for two classes. So we only need to, those are the normal things that we have detected. And for new data we use the support vector boundary learned, and we see this is outside the boundary, then this is an outlier. If it's inside the boundary, it's a normal data. Questions?
So
yes.
If you have the support vector trained to find what is in the boundary, and then is that then sensitive to the fact that if you have a new data point that is maybe outside the current boundary, but it's supposed to be a normal class?
Right. So again, in the support vector, when we discuss the support vectors, there is a slack variable and a cost parameter, remember? So the combination of cost and slack variable would allow this boundary to be flexible. You can decide how many things that you want to include, how many things you has to be put it as outlier. What I'm saying is you can adjust this boundary to make this this rough ball bigger to include more examples in the normal and leave out less outliers.
Thank you.
But again, it will not, because you're not labeling, you don't have, it's not because you choose to use one class support vector when you have two sets of labeled data. You would pick this method only when you don't have negative data labeled negative data. Because one class model only have training example for one type of data, its performance cannot be directly compared to the two-class classification methods.
So if you had labels saying this is
yes,
the outlier class or minority,
right? You should try to use two-class approach, because that way you offer more information to the machine. The one-class model only works. I mean, it's used when you don't have this extra information that you could provide to the machine. You only have labels for one group. So semi-supervised learning, the idea is because we don't have lots of training examples and we have lots of unlabeled examples. So the idea is to combine classification-based and clustering-based methods. In this way, that we first use a clustering-based approach. So where we don't need label, we put things into cluster. Then we hope we can find a large cluster C and some small clusters, could be one small clusters. In the C, we hope we can find the label normal. So some of the class, we know that we have label for some data, not a lot, but those data are going to be put into a cluster. So if those clusters are large enough, we will think, okay, so this represents the normal class. Then we will treat all objects within this large cluster as normal. And when we can use the one-class model, now we have training examples for normal. We learn a model to identify normal objects. There is a smaller cluster C1, and there is something labeled as outliers in that C1 as outliers. We can declare all the objects in C1 as outliers. So then these outliers and anything that's not fit into the model could also be labeled as outliers. So this is the one way that you could possibly think that clustering and classification models can be used together. There are also other ways you could do it. For example, if you have large and small clusters, one with positive normal labels, one with negative outlier labels, you can pick the cluster with most outlier labels and label everything in that as outliers. And you can find a large cluster with normal data labeled and use that as a normal training example. Then you can actually start to use co-training schemes to alleviate, use active learning schemes to actually ask the algorithms to check for more, label more examples. So there's many different ways that possibly can be applied to tackle this question. So the idea is to make use of a small amount of training examples. Because we have smaller training examples, any of those mechanisms going to produce a result that is probably better than nothing, but probably will not be better than the one when you can actually provide a good number of both positive and negative training examples.